Hello everyone, welcome to our video that covers section 2, probability. In this video we're going to cover some of the basic ideas of probability. A brief overview of the video goes like this. We'll start with the axioms of probability, discuss empirical probabilities, equal outcomes probability, and take a look at some of the counting formulas for probability. So probability is a hard word to define in a formal sense. Many people have a certain intuitive idea of how probabilities work, but if you had to define it, it can be difficult. So one way to go about it, mathematical way, is to identify some axioms that probabilities must satisfy. So here are three important axioms that probability measures or probability functions must satisfy. If we have a sample space S and A is an event, then the probability of A must be greater than or equal to 0 for any possible subset A in S. So it's sometimes called non-negativity. Right? So probability cannot be negative. The second axiom tells us that the probability of S must be equal to 1. So if we look at all the elements in the sample space and calculate the probability of this set, this must add up to 1. So 1 and 2 together do tell us that the probability must be between 0 and 1. And the third axiom just tells us that if A and B are disjoint, then the probability of A union B is equal to the probability of A plus the probability of B. So using these axioms, a lot of statements can be proved. You'll see that in the textbook. But this is sort of where we start the discussion of theoretical probabilities, right? And obviously, we say that P is our function that gives the probability of an event E. But another type of probability that does occur often is the empirical probability. So if we let n of E be the number of times event E occurs in m repetitions of an experiment, then the probability of E is the number of occurrences of E divided by m. This is called the empirical probability of E. So when we use formulas and axioms, we are typically finding theoretical probabilities, but when we use historical data, we're finding empirical probabilities. So here's an example of an empirical probability. Suppose a study was performed to determine blood types in the United States. And the main blood types, as you may know, would be type A, type B, type O, and type AB. And then each of these has a negative and a positive. So we get these 8 different blood types. And you could see here that this is given in order from the rarest to the most common. So 0.6% of Americans have type AB negative, so that would be the rarest. And the most common blood type would be O positive, 37.4% have type O positive. So one example might be, what's the probability a person has type O blood? Right, so here we're looking at negative and positive. So type O blood, if we wanted to calculate that, we would add the 6.6% plus the 37.4% expressed here as decimals. So we get an answer of 0.44 or 44%. So this is a good example of an empirical probability. right? We didn't use any counting formulas, really didn't need to rely on the axioms at all. We're just using historical data, and we get a meaningful probability. Now, when we start really our discussion on theoretical probabilities, it begins with sample spaces where you have equally likely outcomes. So suppose each outcome of a sample space, let's say, is A1, A2, and so on up to AN, and these are all equally likely. So we can sort of actually show, using the axioms of probability, that if I have an event E, the probability of E is equal to the number of elements in E divided by the number of elements in S. So when we calculate probabilities like this, we're finding what I would call a theoretical probability. And when we approach it like this, the probability question essentially becomes a counting problem. So a couple of counting formulas I just want to mention. There are more counting formulas than these, but I just want to make sure everybody is familiar with these. We have the permutations, right? So in general, there's n factorial permutations, or number of ways to order n distinct items in a row. Right? For example, if I wanted the number of different spellings of the word number, right? There are 6 letters in here. The letters are all distinct. So the number of sequences we can make using these letters would be 6 factorial. This is the type of counting problem that does come up when order is important, and we will be talking about these, if not in this section, in a little while. Then we have combinations. Okay, so n choose k gives us the number of different subsets of k items taken from a set with n distinct items. And there are various ways we could calculate n choose k. One formula is this is n factorial divided by k factorial times n minus k factorial. And you can see there's a sort of symmetry here. N choose k is equal to n choose n minus k. So one example might be if we wanted to know the number of committees of size 2 in a group of 10 people, then we would calculate 10 choose 2. So this would sort of simplify to 10 times 9 over 2 after we did some canceling, and you can see we get 45. The third counting formula that I'll mention here is one that we've talked about in the earlier section. It's just the principle of inclusion-exclusion. If we wanted the probability of A union B, we get the probability of A plus the probability of B minus the probability of A intersect B. Okay, so we'll finish this video with an example. And I'm going to think about a random number generator function. So almost all software languages have this, but let's keep it simple. If we use Excel, then Excel has a function called ranBetween. And the first number we enter would be a lower bound. The second number we enter would be an upper bound. So if I wanted to generate random numbers between 1 and 100, I could use this function, right? This will generate numbers, including 1 and 100 as a possibility. And with this random number generator, each number is equally likely to occur. So suppose that a random number is generated. Okay. Now I'm going to ask you to stop the video and try to find answers to each of these questions. It shouldn't be too bad. So the first one is find the probability a multiple of 5 occurs. The second is finding the probability of a prime number below 50. The third is to find the probability that a perfect square occurs, right? So the perfect squares are 1 squared, 2 squared, which is 4, 3 squared, which is 9, and so on. D asks for the probability that you get a 2-digit number with the same 2 digits, or in other words, multiples of 11. And the last one asks for the probability that you get a multiple of 5 or 7. Okay, so let's see if you could get these. My guess is you could probably get most of these, perhaps all of them. Okay, here are answers. So if you wanted the probability of a multiple of 5, there are 20 of them. You could start listing them out. 5, 10, 15, 20, and so on. You should count 20 of them. Or another way to do it is to take 100 divided by 5, and you see you'll get 20. The primes below 50. Okay, so here is a situation where you most likely have to make a list. So here I've sort of listed the primes below 50, right? We have 2, 3, 5, 7, and so on, up to 47. I counted 15 of these. So the probability of generating a prime below 50 is 15 over 100. And similarly, we can make a list of the perfect squares. You could see these go all the way up to 100, 1 squared, 2 squared, and so on, up to 10 squared. So we get 10 perfect squares over 100, and that is our probability. All right, in part D, we wanted the multiples of 11. So it's easy to see that we go from 11 to 22 and so on up to 99. We get 9 over 100. Now part E requires the use of the inclusion-exclusion principle. At least that's the quick way to do it. You could try to brute force this and make lists, but it's fairly straightforward to use inclusion-exclusion. The idea is first you count the multiples of 5, and we know there's 20 multiples of 5. Then we count the multiples of 7, okay? And you'll see there's 14 multiples of 7. But if I were to add the 20 multiples of 5 and the 14 multiples of 7, I would count the numbers that are multiples of both 5 and 7 twice. All right, so the multiples of 5 and 7 would be numbers like 35. And then there's another one, there's 70. And that is it, below 100. So there are 2 multiples of 5 and 7. So using an inclusion-exclusion will be here in the numerator. You see we get 20 plus 14 minus 2. So we get 32 over 100. So that concludes this video. I hope you've enjoyed it.